Okay, well, we're going to continue our program in just a moment with Heather Turner, who is joining us to talk about a common but I find difficult type of data, which is ordinal data. And we have rankings of personal preferences or people winning a race. How do we deal with data like that? And I hope to learn a lot from Heather about what we do. Thank you, Heather.
Thanks very much. Yeah, if you want to have a look at the slides, they're on Git Pitch on this link. So I'll just leave that up a second or two before I switch to them myself. Okay. So yeah, I'm going to be talking about modelling item worth based on rankings. And this work was motivated by a project with Jacob Van Etten, who works in Costa Rica in agricultural development. And we also had help from David Firth and Yanis Kosmitis on the programming and statistical methodology. So as David said, I'm talking about rankings, and you can imagine rankings arising in sort of various different settings, such as athletes and where they finish in a race, or preferences that somebody expresses about a product. But I'm really thinking about cases where we have lots of these rankings. So if we just have a single ranking, well then that's it. But what do we do when we have lots of rankings, and how do we get the information from that to decide what the worth of each item is? So a classical way to approach this problem is to work from Luce's axiom. And this states that the probability of choosing one item, say item A, over another item, item B, is unaffected by the other items. So if I say I prefer Coca-Cola to lemonade, that's going to be the same if you just give me the choice of those two items, or if you say, well, please rank Coca-Cola, lemonade, and Fanta. It doesn't matter whether Fanta comes first, second, or third. I'm still going to put Coca-Cola before lemonade in my ranking. So it's a reasonable sort of basis, and it turns out that a mathematical consequence of this axiom is that if we have a set of j items, as we've got here, I1, I2, up to ij, then the probability of selecting any particular item j from that set is given by this quantity here, where we've got a parameter alpha j representing the worth of the selected item, and that's we've got the ratio of that against the sum of the item worths for all the other items in the set. So that's just for a single choice of one item out of a set of j items. So we can build on that by thinking of a ranking as a set of a series of choices. So first we choose the first item out of all the possible items. Then once we've done that, we put that to one side, choose the second out of the remaining items. And so you can see, if you've got sort of mathematical background, it's fairly simple to come up with this model, where we just take the product of the probabilities for the individual choices to come up with the probability of a particular ranking. And so this is called the Plackett-Luce model. It was independently proposed by two different guys called Plackett and Luce. And what I'm presenting today is a package called Plackett-Luce that can be used to fit this model. So let's look at an example using data that was released by Netflix for the Netflix Prize. They released lots of movie rankings in a competition, and we're just going to look at a small subset here of rankings of 4 movies. And there's a little helper function in the Plackett-Luce package called read.soc, which reads these rankings from a file in a particular format that's used on preflib. So I've got the web address here for preflib, which is a library of preference data. So it's various standard data sets that the community have shared to work on modelling and so on. So we can read in this data using this read.soc function, just directly offline. And the result is as shown at the bottom here. So this is just showing the first couple of rows. And each row is the first column is a frequency. So they're saying we've got 68 of the first type of ranking. And then we've got the ranks in the column. So the first row says that 68 people rank the second movie first, then the first movie, then the fourth movie, then the third movie. Okay, so this is rankings in the form of orderings, where we have the items per rank. What we'd like for our placket loose package is actually to do it the other way round and to give the right rank per item. And you could do this by just sort of putting the items in the column and putting the relevant ranks in the data matrix. But we offer a little function called as.rankings to create a special rankings object. And that's what I'm doing here. So I'm just taking out the frequencies for the time being, saying that my data are coming in the form of orderings, so orderings of the items, and creating a rankings object. Our read.soc function also collects the names of these items. So here they were just called item 1, 2, 3, 4, but we were talking about movies, so they're saved in an attribute which we can then add to the rankings object in the underlying in the column names of the underlying matrix object. But one of the advantages of creating a special type of object is we can have things like print methods. So if we print out the first few rankings, we get a fairly sort of user-friendly printout. So we can see that the first ranking actually corresponds to Beverly Hills Cop being ranked first, then Mean Girls, then Mission Impossible 2, and then the last one sort of gets knocked off, but you can change the width to see longer ranking and so on. So now once we've got our data in that format, we can fit the placket loose model. And in this case, it's fairly simple. We just pass our rankings object to the model fitting function placket loose. And now we bring back our frequencies and supply those as weights to the model. Then if we call the coef function, which is a method for models fitted by placket loose with log equals false argument, we get coefficients of this type. And these are the worth parameters that we had in the model formulae a few slides ago. And in particular, they're constrained to sum to 1, so they can be directly interpreted as the probability that a particular movie is ranked first. So we can look at these movies and say there's 45 probability of 0.45 that Beverly Hills Cop will be ranked first. At this stage, we're just coming up with point estimates. If we want to do some statistical inference, it's better to work on the log scale. And we can, in that case, we set a particular parameter to 0 to represent the reference. So in this case, we're setting Mean Girls as the reference movie. And then we've got the log worths as the points here. And these intervals are based on methodology implemented in QVCalc, which is a package that's been around for a while. And what that allows you to do is estimate a similar thing to confidence intervals, but they can be defined for all the items, including the reference item. So for all the items, we can get a 95% comparison interval, and they work as you might expect. So if they overlap, there's no significant difference. If there's separation, we can say they're significantly different. So in this case, we can say Beverly Hills Cop was significantly preferred over all the other movies, and then Mean Girls, but the other two movies, The Mummy Returns and Mission Impossible 2, they're much of a muchness. There wasn't a significant difference between them. So that's the standard placket loose model, and it deals with strict complete rankings. So what do I mean by that is that there's no ties in the data, there's a strict ordering, and all of the items that we're considering are appear in every ranking. But in other applications, we might get ties. That's quite common, of course, in races and other applications. And we can have two different types of incomplete rankings. So we might only present a certain subset of items to a person and ask them their preference over that. Or we might have a large number of items, and it's unrealistic to ask people to rank them all. So we say, just give us your top 5 or your top 10. And placket loose can handle both of these. In particular, it implements a generalized model which will handle ties. The mathematics gets a little bit more complicated, but you can see that the structure is the same. So now, instead of individual items in our ranking, we've got sets. So these objects, these sets, C1, C2, might be an individual item, or they might be two items. And if it's more than one item, we're saying that those items are tied. If it's preference data, there's no preference between those items. And then we work that through in our model. So now instead of having an individual worth, we have a function of the items in the set. So if we think of our model as a product of the probabilities of each choice, then on the top we've got a function of the set that's chosen, and that's given by this expression at the bottom here. So if we've got two items in a set, we multiply their worth and take the root according to the number of items that are in the set. And there's a new parameter that comes in here, the delta parameter, and that's related to how often we see ties of this order. And we only consider up to the maximum order that we see. So if we only ever see ties of two items, we only consider the possibility of having two items. And that becomes important when we have to think about all the other possible choices we could have made, because what this sort of complicated summation is doing there is it's saying, we could have chosen any other individual item, or we could have chosen any other pair. We have to have all the different combinations of the pairs or the triples, or up to whatever order of ties we want to consider. Another problem that can happen in using the Plackett model in sort of real applications is that the underlying network of wins and losses implied by the ranking can not be sufficiently connected so that we can't estimate the maximum likelihood. So here's a couple of cases where that happens. So in this network diagram, a double-headed arrow means that there are cases where A wins against B and when B wins against A. But in terms of D, we only ever observe D to lose. And so if we think about the log worth, there's no bound on how low that can go. So the maximum likelihood estimate is actually negative infinity, and is not particularly useful. In other cases, we can have completely disconnected networks. So we'll have some comparisons between one set of objects, say D and E here, and other comparisons between another set of objects, A, B, and C. And we can compare within those clusters, but we have no idea how those two clusters relate to each other in terms of their relative worth. And the Plackett-Luce package deals with that by introducing a ghost item, G, and adding pseudo-rankings to the data where each item wins and loses against this ghost item. And that means the network is always connected, and the maximum likelihood estimate is always estimable. And this can be viewed as a sort of Bayesian, a simple sort of Bayesian analysis, where our prior is that all the items have equal worth. And the more pseudo rankings we add, the stronger that prior will be. And the default is actually to use half a pseudo ranking. So we don't even have to use a whole number, because if you remember, our frequencies appear in the model just as a weight. So there's no reason why that has to be an integer. So we always use a small amount, and even if the network is connected, this has a beneficial effect in terms of having a shrinking effect and reducing the bias of our estimates. And then a final issue, or I'm sure there are other issues, but the last issue I'm going to talk about is the issue of heterogeneity. So far we've just assumed there's sort of one true ranking, an item has one single worth. But in fact, the worth of an item might depend on the conditions. For example, characteristics of the judge that is making the ranking. And Plackett-Luce works with PartyKit package in order to do model-based recursive partitioning. In other words, to create a Plackett-Luce tree. So how this works is, first of all, it fits a Plackett-Luce model to the whole data, and then it tests the stability of those worth parameters with respect to some covariates. So if we've got some covariates about the rankings, for example, the gender of the person that was expressing the preference, then we can see if the worth is stable across the values of that covariate. And if there's significant instability, we can split the data just a binary split along that covariate. And we just carry on doing that until there's no significant instability anymore. And this was actually the case in our motivating example, which was a citizen science trial of bean varieties in Nicaragua. So in this study, there were 11 bean varieties, but each farmer was only asked to grow 3. They were asked which was the best and which was the worst, so this implies a ranking of 3. And they were also asked to compare each variety to the local variety, so there's also these pairwise comparisons. And alongside that, we have covariates on the growing conditions. And the full study had a larger number of covariates, but we're just going to look at 3, the growing season, the year, and the maximum night temperature. So it takes a bit of work to organise the data, and we've got this work through on the Beans help page. But just to sort of give an idea of what goes on. In the original data, we have it organised in 842 rows, which was the number of farms. And so for each farm, we have 1 3-way ranking and 3 2-way rankings. And these are collected together in 1 complete rankings object for all possible varieties. So there's 11 varieties, and at the top here in the first ranking we've got a 3-way ranking, and at the bottom we've got the 2-way rankings. But we need to relate that to our covariates somehow, and so we have another structure in the package called grouped rankings, which relates these rankings with a variable or a factor that's indicating which farm those rankings correspond to. So now if we print that, instead of having a single ranking in each element, here we've got the 3-way ranking, the first 2-way ranking, and there'd be 2 more pairwise rankings in that element of the data. Then we can pass this to our function PL tree to fit the placket loose tree. And we specify some conditions about how far we should go with the tree. And this is the result. So what we found was that the first split was according to the maximum nighttime temperature. So there was, if there was a particularly high nighttime temperature, there was a slightly different preference of the varieties. So varieties 2 and 3 and 8 were the most popular. Then at the lower nighttime temperatures, for most seasons, varieties 8 and 9 were preferred, but in one particular season, Primera 2016, variety 7 and 9 were the most popular. So this is useful information because it shows, not just which varieties the farmers preferred, but how that relates to the conditions that the farmers are trying to grow the varieties in, and then that can influence what varieties are taken on. So you're not necessarily taking on the variety that's best overall, but you have some information about what varieties you can recommend to particular farmers. So that's a sort of overview of what the package can do, and we have a few ideas of further work we'd like to do, and we already have plans. There's an MSc student that's going to be looking at incorporating spatial effects, and I hope to be looking later in the year at incorporating genotype information. Placket Loose is on CRAN and GitHub, and there's even more detail in the vignettes if you'd like to follow up. Thank you.
Thank you, Heather. That was outstanding. We have time for one quick question. If anybody from the audience has a question for Heather. Anybody out there? I have a question, though. I wasn't sure if you touched in your talk, but what about the situations where there are only partial rankings? Like, if, for example, Netflix asked everybody to rank their top 5 movies, would you be able to use that to get an overall ranking of all movies?
So it's doable with the Placket Loose package, but at the moment we don't support those sort of top-end type rankings. So in the example I presented, we had the case where farmers were only presented with a subset of varieties. They only asked to rank 3 at a time out of a possible 11. But we haven't had the case where people have had to consider all all movies they've ever seen and select their top 10, for example. Yeah.
Thanks, that's very interesting. Let's thank Heather once again.